All right, everyone, welcome back. This is episode 3 of me trying to teach myself C++. This should be an exciting episode because I'm finally going to try to learn about memory in C++. So I have a few things I want to go over today. First one being pointers and references. I want to touch on stack versus heap memory. And I think at the end, if we have time, I will try to look up how smart pointers are used in modern C++. I quickly skimmed through some of this information on stack versus heap, but I will get to that later. First, I want to basically try and see where I'm at with my understanding. A few years ago, I took a very quick class in C programming, and I learned a little bit about pointers and memory, but to be honest, I don't really remember anything about that other than the concepts, and I want to see if I even still know how to create a pointer in C++. So let's start off with making a new directory. We can call it memory. Oh. Yeah, memory, and then we can create a memory.cpp and open that up. Okay, so let's include our IO stream, int main, and let me just figure out how to even use pointers. So from what I can recall, a pointer is a variable, and this variable basically only stores a memory address. Yeah, and depending on the type that we give this pointer, that will tell, I guess, the compiler how large is the data that we're storing at this memory address that the pointer is representing. And so, for example, if we have an int star, this is how we declare a pointer named p, and it is of type integer. And the star basically means that this variable named p is a pointer. And at this point, we've declared that there is a variable p, and it is a pointer. But this variable doesn't actually hold any, we haven't told the program what the value that we want to store at this memory address is. So we can do that with the dereference operator, which is also star. And I believe if we want to set the value of our integer to be 10, we can do it like this. So what's happening here is basically we are declaring that we have a pointer named p of type integer. And here we're grabbing the, I guess, reference to that location in memory, and we're setting it equal to 10. So let me just make sure that this runs, and we can try to print out, let's print out the value of p and see what this gives us. I believe it should be a memory address. So let's compile it here with G++. Our output will be memory, and we can concatenate our run command. Okay, so exactly, we have the console logged a memory address, and if we run this again, I'm guessing it'll be a different address every time. That's correct. Okay. So that's pointers. And let's see. I want to learn about the reference operator. I'm not even sure how that's used, to be honest. Well, first of all, if we wanted to print out the value that we set p, I guess this is how we would grab the value. We would say we want to print out star p. Yeah, so then let's test that out, and it prints 10 because that's the value we set here. Okay, great. Now, as far as the reference operator, let me think about what this means. Let's say that instead of creating a pointer, let's say that we just made a variable x and set it to 10 again in this case. I think that if we wanted to then manipulate this variable by manipulating the memory address, this is when we would use the dereference operator. And that's when we want to store. So basically what I'm saying is if we type reference operator of x, I think this is basically the same as saying the memory address of x. And we can store this, I think, in a pointer. So maybe I'll call it x pointer equals the memory address of x. I think this is correct. And let's see what happens when we try to print x pointer out to the console. So it printed a memory address, and that makes sense, right? Because this is what we're doing. We're storing the memory address in this variable called x pointer by dereferencing the variable x, and then that's what we're printing out. And again, if we run this multiple times, we're getting a different memory address each time because this is just randomly allocated when the program is run. Yeah, that's correct. Okay, so that is the reference operator. Now, another thing, I guess what's the whole point of this is basically maybe for performance reasons. I guess there's lots of reasons, but I think one way to illustrate this is through if we had a helper function. So let me define another function here. Let's just say int, let's call it add. And let's say add takes in two variables a and b, and these are integers. And quite simply, we can just return a plus b. And in our main function, we can, let's create two numbers a and b. Well, they don't have to be called a and b. Let's call it int x, int y. And we'll just set x equal to 10 and y equal to 20. And if we call add and pass in x and y, and we can set the value of a variable called sum to the result of calling add on x and y, I believe that we can print this out. And then add an end line character. So what's going to happen here? Basically, we are passing in 10 and 20 into this function add. And up here in this function, it is going to return the result of 10 plus 20, which should be 30. So hopefully when I run this function, we should see 30. Yeah, so that works. But what's actually happening here, I believe, is that by default, when we pass in data into a function through a regular function call, we're passing in the value of x and y by copying it into their own like memory address. So that's opposed to basically being able to pass them by reference, which is how like languages like Python work by default, actually. So technically, I guess you would call this quite an inefficient function because we're actually allocating extra memory for the values of this variable and this variable when they are being called or evaluated through this function call, if that makes sense. So I think that the way to avoid passing by copy and to in fact pass by reference, I think the way you do it is in our function signature here. We can use this reference operator. And what this is doing is telling this function, this add function, that when we pass in our variables, we're passing in references to these numbers rather than copying their values into this function scope. Now, I don't actually know if this works. Do I just pass in these variables, or do I have to pass in pointers? I'm not sure. Let's see what happens when we compile, I guess. Okay, so it looks like it still actually works. Yeah, so let's see what happens if I try to pass in pointers actually. So let me call let's call this a integer pointer, x pointer equals the address of x, and let's do the same for y. I don't actually know what will happen if we do this, but let's just test it out. Okay, so actually it's giving us a linting error because these are not the correct type that the function is expecting. Okay, I think that makes sense. So actually when we're passing in by reference with this, using this syntax or this notation, the function is actually expecting us to pass in the values, or like the non-pointer variables that we want to represent A and B with. Okay, cool. And one other thing I want to demonstrate is by doing this and having a function take in references, this actually enables us to modify these variables and yeah, basically modify them inside of the scope of this function, and then we can see that outside of the function that those variables are also being modified, which is not the case when you're passing in by value. So let me think of an example. Let's say if we created a function called increment, and this this function will take in an integer. For right now, let's just make it take in a copy to demonstrate a point, and we can say actually this will not return anything, but we can say inside of this function we want to increment number. So I believe that if we keep it this way and we're taking in a copy of the value, this function, even though we're incrementing this number, this variable number inside of this function, if we were to call it outside in our main function scope, modifying this value inside of this function will not modify it when we check it outside of the scope. So what do I mean by that? I guess we can say we'll just deal with integer x, and let's say that I wanted to increment x and make x equal to 11. So I could call this function increment and pass in my variable x, and you might expect to see that the value of x gets incremented. So you might expect to see 11 when we print it out. So let's run this. And in fact, we actually see that x has not changed. It's still equal to 10 when it is printed out. But if instead in our increment function, we were taking in the reference to a number, what then happens is we're passing in basically the memory address so that this function knows it's going to actually modify the value that is associated or like pointed to by that memory address. So I think if I'm correct, x should become 11 when we run this. Perfect. Okay. So I think, yeah, my understanding seems correct. And then I think next we can talk about, so we went over pointers and references, and then I think I'll touch quickly on stack versus heap memory. For stack versus heap memory, let's skim through this article really quickly and see if let's see if it makes sense. So in C, C++, and Java, memory can be allocated on either a stack or a heap. Stack allocation happens in the function call stack, where each function gets its own memory for variables. In C and C++, heap memory is controlled by the programmer, as there's no automatic garbage collection. Stack allocation refers to the process of assigning memory for local variables and function calls in the call stack. It happens automatically when a function is called and freed immediately when the function ends. Since memory is managed by the system, it's fast and efficient, but it has limited space compared to heap allocation. If too many function calls exceed the stack's capacity, it results in a stack overflow. How it works: memory is allocated in contiguous blocks within the stack. The size of memory is already known before executing. When a function is called, its local variables are allocated on the stack. Once the function finishes executing, the allocated memory is freed, so we don't need to worry about freeing the memory. Okay, that seems like that makes sense. In the example code int main, all of these variables get allocated on a stack. I'm assuming because this is happening in our main function, and it said all of the local variables are stored on the stack. Local variables are allocated on the stack. Okay, in contrast, we have heap allocation. Heap memory is allocated dynamically during program execution. Unlike stack memory, heap memory is not freed automatically when a function ends. Instead, it requires manual deallocation or a garbage collector in Java or Python to reclaim unused memory. Heap is not related to heap data structure. It simply refers to a large pool of memory available for dynamic allocation. Whenever an object is created, it is stored in heap memory, while references to these objects are stored in stack memory. References to these objects are stored in stack memory. Okay. Heap allocation is less safe because heap data is accessible by multiple threads, increasing the risk of data corruption and memory leaks if not handled properly. Okay. Skip over this stuff. If heap memory is full, JVM throws an error. Unlike stack memory, automatic deallocation does not happen. Okay. So heap is dynamic memory. There's more of the memory, more space in the heap, but it's very manual. So you need to make sure that we clear memory from the heap if we allocate memory from the heap. Stack memory is handled automatically through the function call stack. I think that's what I'm drawing from this. Constructor call and memory allocation. Okay, don't really understand that part. Let's see, in a stack, it's kind of saying the same thing over and over again. All right. I think where this comes into play is from what I've read in another page. Basically, when we're working with classes and creating objects, let's say that we have a class named car. I think that when we create a new car object, such as car, my car. I can't remember. I think if we do it like this gets created maybe on the stack. But I remember if we use the new operator, I think this puts it on the heap. But we just haven't defined a constructor, so that's why this is not working here. So let me actually ask Gemini about this. So I asked, when creating an object, does it default to allocating on the stack? Does the new operator create it on the heap? It says yes, there's a predictable set of rules. Stack allocation by default. When you declare a variable like a standard local variable, it is automatically allocated on the stack. So they said my class object is allocated on the stack, and then at the end of the function scope, it's automatically destroyed. So that's what they mean by lifetime. Performance is very good. Size limits, the stack is relatively small, 1 to 8 megabytes, depending on the OS. So large objects or arrays can cause overflow. Heap allocation. When you use the new keyword, you are explicitly requesting memory from the heap, also known as the free store. So they are creating a new myClass object. And you must remember to free this memory when you're done using it, basically. So they're using the delete keyword here, I guess. But I believe if we define this class, we could make a destructor, which I think is how we might automatically handle clearing that from the heap. Not actually sure about that. A note on modern C++. While new is how you access the heap, modern C++ discourages using raw, new, and delete because it's easy to forget to clean up. Instead, we use smart pointers. Okay, so great. This is what I was talking about before in our notes. So standard unique pointer is for exclusive ownership, and standard shared pointer is for shared ownership. These live on the stack, but manage an object on the heap. Okay. Which gives you the best of both worlds. Heap-sized memory with automatic stack-based cleanup. So, okay, so these pointers, which are just variables, memory addresses, these pointers that point to objects are living on the stack, so they're automatically cleared when we're done with them. But we can use these pointers to basically like control memory that is being stored on the heap. And we don't have to worry about clearing that heap memory because once the stack clears the pointer, I guess the memory that's allocated on the heap just basically becomes garbage, and can be used again because we're never going to access that memory again. Cool. Okay. All right. I think that is a pretty good stopping point, and I think I'm gonna have to I'm gonna think of a project that we can do for next episode. And then yeah, thanks for watching, everyone, and we'll see what happens next time.